Evening everyone, and welcome back to ZDMA News. My name is Zarina and we have some updates for you all back at home. Turbo machines, what are they? Who are they? Let's dive into it. Well, if you didn't know, turbo machines are dynamic fluid machines that work to either add or extract flow energy. When you're adding energy, using a pump, and when you're extracting energy, use a turbine. But what's really the difference? I'm glad you asked, so let's find out. When it comes to pumps, always remember they do work on the fluid to move and increase the pressure of the fluid. A common example of a pump would be a propeller on an airplane or even a ship. On the other hand, when it comes down to turbines, the fluid does work on them. Common example for a turbine would be a windmill. So we briefly discussed the difference between a turbine and a pump. Let's backtrack and look at the components that make up a turbo machine. Turbo machines consist of a rotor attached to an input and output shaft and several blades that form flow passages. Turbo machines can be categorized in 3 sections: axial flow, radial flow, and mixed flow machines. But what's the difference? You keep asking me these questions, I'm going to have to answer. When the flow is parallel to the axis of rotation, they are called axial flow machines. When flow is perpendicular to the axis of rotation, they're referred to as radial flow machines. And as the name suggests, mixed flow machines exhibit a combination of both properties. Let's get into the nitty-gritty and begin understanding the work transferred to and from a fluid through a turbo machine. Please consider again a fan blade. We have the blade speed, the absolute fluid velocity from a stationary viewpoint, and the relative velocity as seen by riding the fan blade, all of which are connected through the fact that the absolute fluid velocity is a vector sum of the relative velocity and the blade velocity. The importance of these components come into play with a set of equations under the name of the Euler turbo machine equation. Starting with equation 1, shaft work is directly proportional to the mass flow rate and depends on the tangential component of the absolute velocity. Equation 2 here is the shaft power, which is derived from the fact that shaft power is related to the shaft torque and angular velocity, and if we recall correctly, the blade speed is also related to the angular velocity and distance to the axis of rotation. Equation 3 represents work per unit mass, which is simply shaft power divided by the mass flow rate. These 3 equations represent the basic equations for pumps or turbines, regardless of the direction of flow for any fluid. I've just received word from our producers that there's more to this story and I've only scratched the surface. So please welcome my co-anchor.
Thank you, Zarina. Right now, I'm here at Pact Enterprises, and I can truly say it's a disaster. Throughout the grounds, centrifugal pumps are overheating and burning the arms of workers. Depression, they are burning their legs. To try and figure out what happened and what went wrong, we're going to pass it on to a worker at Pact Enterprises who will explain how centrifugal pumps work.
A centrifugal pump is a turbo machine that uses rotation and centripetal force to function. Looking at this picture, a centrifugal pump consists of 2 main parts. First, we have the impeller, which is located in the center and rotates uniformly while the fluid being pumped enters the inlet. When the fluid does enter, it's important to note that we want the fluid to flow in an outwards direction. To achieve this, we add blades along the impeller to help move the fluid in such a way that it creates a centripetal force. As the fluid rotates and the blade moves the fluid outwards, the fluid will leave the impeller at larger amounts radially as the casing surrounding the impeller increases in area. The fluid then leaves the outlet at a rate of Q. Some other important information to know are the characteristics of the pump. When looking at a centrifugal pump, some characteristics we are concerned with are the head rise, power, and efficiency. The head rise, or the amount of possible pressure rise by a pump, is equal to H2 minus H1, where H equals this equation. We also care about the power that it takes to drive the pump. This depends on the work that is being done on the fluid and the flow rate. The equation that covers this is power equals rho GH cubed. Last, we have the efficiency of the pump, which equals the power gained by the fluid divided by the shaft power driving the pump.
Thank you, mysterious worker. While we may not know what exactly caused the overheating, we do know more about these pumps. That's for all, and now to Danielle for her segment on AcidCo.
Breaking news. It seems like AcidCo, the multi-million-dollar corporation, when building their new plant in Bluesdale, didn't take similarity laws into account when assembling their pumps and just free-handed it. It caused a drainage failure, resulting in chemicals leaking into the surrounding town's water supply. Hundreds dead. For those who have no idea what any of that means, I have our specialist back on base who's going to get into it.
So first, we're going to discuss dimensionless parameters and similarity laws, and as my colleague Alexia has mentioned, the main dependent pump variables are the actual head rise, shaft power, and efficiency, and following a dimensionless analysis, we would achieve the dependent pi term. The dimensionless parameters formed are referred to as the head coefficient, the power coefficient, and efficiency is already dimensionless. Of the 4 independent terms, 3 of the 4 can be neglected. So that leaves only one term that they're dependent on, which is CQ, the flow coefficient. So if 2 geometrically similar pumps are operated to the same flow coefficient value, then all our dependent pi terms would follow, such that the head coefficient, power coefficient, and efficiency would be the same, and these can be referred to as the pump scaling laws. Now these are the graphs for typical curves for a centrifugal pump, and the same results in terms of dimensionless coefficients, and we're going to use them to solve an example. Based on the pump scaling laws we discussed before, we're going to be predicting the discharge, actual head rise, and shaft horsepower for the peak efficiency of an 8-inch diameter centrifugal tube operating at 1200 rotations per minute. And it's geometrically similar to the 12-inch diameter tube, having the performance characteristics shown in the figures below, with the left being the regular characteristic curves and the right being the dimensionless. So for a given efficiency, the flow coefficient is the same for a family of pumps, being these 2 pumps, and the flow coefficient on the graph is 0.0625, as shown here. And then, based on the rearrangement of the flow coefficient equation, for the 8-inch pump, it would be equal to the flow coefficient times the rotational speed times the diameter cubed, which would give us 2.33 feet cubed per second. And then in order to calculate the actual head rise, we'd rearrange the head coefficient equation, and at peak efficiency, CH is equal to 0.019, as shown here. And then the rotational speed is 126 in the units of radians per second, so the rearrangement of the equation for the head coefficient would give us 41.6 feet. And then in order to calculate the shaft horsepower, we'd rearrange the power coefficient equation. And based on the graph, CP is equal to 0.014, as shown here at peak efficiency. And the rearrangement of the equation would give us that the shaft power is equal to the head coefficient times the density times the rotational speed cubed times the diameter to the 5th power, which would give us 7,150 feet pound per second, and converted would give us 13 horsepower. Pump affinity laws that discuss how geometrically similar groups of the same flow coefficient vary, and the equations follow as such, with diameters being the same, how the variables vary with speed, and with rotational speed being the same, how the variables vary with diameter. Another useful dimensionless parameter is specific speed. A modified version is used in the US as the NSD, with different units, and as shown, if the required head, flow rate, and speed are specified, you can select the most efficient pump geometry, whether it be radial, axial, or mixed, for a particular application. Now that we've covered dimensionless parameters and similarity laws, we're going to talk about some of the other types of pumps, aside from centrifugal, that these parameters and laws would also be applicable to. And a commonly used one is the axial flow pump, and they're mainly used for applications requiring drainage or irrigation, since you'll need high flow rates at low heads, and centrifugal pumps aren't suitable. The flow is parallel to the shaft and moves past the rotor blades and is straightened more by the stator blades. Mixed flow pumps have both radial and axial components and are used for applications requiring intermediate specific speeds between 400 and 900 to operate efficiently. A biomedical application of pumps would be the LVAD, which supplements a diseased heart and can either use centrifugal or axial flow for continuous flow of blood. Now, pumps and fans operate the same way, but pumps are used for liquids while fans pump air and other gases. But rather than the head rise, the pressure rise is used for fan performance data. The scaling relationships used for pumps are also applicable to fans, so the new relationships would be reflected in the pressure rise.
Now that our specialist has covered the different types of pumps and fans, along with the similarity laws using dimensionless parameters, I hope you've gotten an idea of why that drainage failure happened. If not, oh well. I'm gonna pass it over to Marian to get into turbines and what happened at the Prairie Farm.
In recent news, power at Prairie Farm has completely shut down. Investigations revealed that the reason for this power outage is from the water wheel breaking down. We have an expert on the scene.
Hi, news reporter Marian. I'm here on the scene at Prairie Farms called in to give a comment about the broken water wheel. Before I get down to the nitty-gritty, nasty, icky little details of how this went horribly wrong, I wanted to teach you a thing or two about turbo machines.
I know everyone is excited to hear about turbines. Turbines are devices that extract energy from a flowing fluid. They can be classified based on the mechanism of the fluid interaction with the turbine blades. This can either be split into impulse turbines or reaction turbines. Impulse turbines are characterized by the force on the blade being produced solely by the turning fluid, with all of the pressure drop occurring in a fixed nozzle. On the other hand, for reaction turbines, some of the fluid vane force is from fluid turning, and some of the force is a reaction to acceleration of the fluid relative to the vane. One important thing to note is that the pressure drop occurs in both a fixed nozzle and in the moving vane. To characterize turbine blading, you can use degree of reduction, which is the ratio of the drop in static pressure or enthalpy across the moving blade to the overall drop in static pressure or enthalpy across a fixed nozzle and the moving blade. A degree of reduction of 0 is characteristic of impulse turbines, whereas a degree of reduction from 0.1 to 0.7 is characteristic of reaction turbines. Now let's get into some examples of impulse turbines. First up is the Pelton wheel as shown. Some important things to note are that the total head of the incoming fluid is converted into a large velocity head at the exit of the supply nozzle. Pressure drop across the bucket, which is the blade, and the change in relative speed of the fluid across the bucket are negligible. And also, the impulse of the individual jets and fluid striking the bucket generates torque. One main characteristic of the impulse turbines that you will see is that the space surrounding the rotor is not completely filled with fluid. Moving on to talk more specifically about the Pelton wheel, we will see that it is characterized by tangential flow. One important thing to note is that water velocity doesn't change, but direction does. This change in direction of velocity causes a torque on the rotor, resulting in power output from the turbine. As we analyze the inlet and exit velocities, we can get equations for the power, the mass flow, and the velocity going on in the system. Some important points to note is that velocity at max power occurs when velocity is divided by 2, and this also occurs when the change in power relative to change in velocity is 0. Max speed also occurs when T shaft is 0, which means that the load is removed from the turbine. We can also see that U equals omega R, which equals V1. This means that the turbine is freewheeling. Here, the water simply passes across the rotor with no force on the buckets. For another example, we have the multi-nozzle non-pental wheel impulse turbine that exhibits axial flow. For example, you will see this in dental drills. In addition, the fluid that is usually correlated with this system is air. Some important characteristics to note are Rm, which is the arithmetic mean radius. This is the average radius between the blade tip and the blade base. In addition, power is equal to negative U1 times V1 plus U2 times V2. For this case, the mean radius velocity makes power equal to negative 2U squared. In addition, it's important to remember that the rate of power is equal to the mass flow rates times power. While impulse turbines are best suited for lower flow rate and higher head operations, we can move on to reaction turbines, which are best suited for high flow rate and higher head operations. In a reaction turbine, the working fluid fills the passageways through which it flows. Angular momentum pressure and velocity of the fluid decrease as it travels through the turbine rotor. Here, the turbine rotor extracts energy from the fluid. Moving on to some examples of reaction turbines, we have the radial flow Francis tube and the axial flow Kaplan tube. The main thing to take away here is that the rotor is surrounded by a casing, which is completely filled with the working fluid. Here you can think as the pump is flowing backwards. One important thing to note for the axial flow Kaplan tube is that it reaches tangential velocity and vortex motion before it reaches the rotor, hence why it's considered axial flow. To tie it all back together, we can think about the differences between turbines and pumps. For pumps, they add energy to the fluid. On the other hand, turbines remove energy. However, they do have some similarities. For example, the flow coefficient, head coefficient, and power coefficient are defined the same way for both. On the other hand, turbine efficiency is the inverse of pump efficiency as shown. In order to determine which type of turbine is best for your system, you can also use power-specific speed as shown, and this is going to be a dimensionless value. For values greater than 0 and less than 10, an impulse turbine is optimal. For values greater than 60, axial flow turbines are optimal. However, for intermediate values between 10 and 100, radial and mixed flows can be used.
Now, though that didn't answer your questions about the prairie farm failure at all, I hope it was a useful bit of information.
So, do you know what could have gone wrong?
Well, if I had to guess, I think the wood was old and rotting and couldn't take it anymore. I'm more of an expert on other designs, so I guess we'll never know.
Thank you for your valuable input. Well, that is all, folks, for CDMA News. I hope your day is well and we wish you a wonderful rest of your week.